And I'm an engineer by education, right? No, mine is
Can you hear me? You can sit down, please.
Chandra, can you pull it up?
Well, after that wonderful introduction, I'd better give a decent talk. Thank you very much. I'm going to talk about this Higgs mode in superconductors, and I am somewhat embarrassed to speak about it because it's kind of old stuff. However, that's what I was asked to speak about. This all started by some very interesting experiments done at University of Illinois by Miles Klein and his students in 1980. And this was a time when Raman scattering experiments first began to be done on metals. And this is a rather hard thing to do, hard experiments. These days they are much easier. And he was the first person to do it on a material that becomes a superconductor and observed something. Now by 1980, everything that we could possibly think about on superconductivity had been well understood, but he observed something peculiar. And I worked out a theory of that with a guy who's a postdoc, who just come from England to Bell Labs at that time, Peter Littlewood. And I'm going to talk about that. And this thing didn't get much attention till the Higgs at LHC was discovered. And there were various questions asked of me when that was discovered, so that I thought about a couple more things in relation to what was discovered in the 1980s, and that's what I'm going to emphasize in this talk. The theory that I'm going to talk about, the basic physics, is extraordinarily trivial. The issue is really more interesting is purely the sociological aspect as to why these modes were not discovered. In fact, if you look at the literature on superconductivity in the 60s and 70s, and if you look at the equations with a fresh eye, it's there in lots and lots of papers, but not identified as such, primarily because there was no need for it. It really is not terribly important for the phenomena of superconductivity, while it appears to be crucially important to have discovered it in particle physics. So the most interesting thing is, and there's some physics behind that, as to why it was not appreciated or discovered. Okay? You cannot. That's probably, I have to tap it periodically, I guess. Okay, and that's what I'll discuss. I'll talk about some recent experiments done in France which verified a key prediction of this theory. And then I will make some very uninformed pedestrian remarks on the relationship of particle physics to condensed matter physics in relation to how differently we think of superconducting condensate from the electroweak condensate. Okay. All right. So what was the experiment that Klein et al. Did. They did a Raman scattering experiment. What do you do in a Raman scattering experiment? You have a sample on which you shine light, and this light has some specific polarization which you can specify in relation to the symmetry, point group symmetries of the crystal. This is getting to be a bore. It seems like it wants me to be close to it. So you specify the polarization and the frequency, and if you do a good experiment, quite often the photon comes out with a different polarization and a different frequency, which really means that you have left behind inside the crystal some excitation which can be characterized by a second rank tensor, some kind of product of the incident polarization and the output polarization and this difference in frequency. Okay? I suppose in Texas A&M, I should call it Raman Mandelstam scattering. Is Mandelstam? Is it?
No, Brilvan.
Brilvan Mandel. Raman is all right. Okay, give the poor Indian something. Okay, so you do this experiment in niobium diselenide, and this has a superconducting transition temperature of 7.2 Kelvin, and you do the experiment at 9 Kelvin, and you see a bunch of phonons. Now, this material has a charge density wave transition in which the crystal structure changes its symmetry, the zone doubles, and therefore, due to the new periodicity, a new phonon appears. So this phonon is absent above 40 Kelvin, but new phonons appear due to this charge density wave, and you see this is a phonon in A1G symmetry. A1G symmetry is sort of the breathing mode of the crystal structure, and E2G is a lot more complicated. There's some motion this way, some motion that way, and even some motion in the third direction. We don't have to worry about it, except that it is a different symmetry. And you see these, and then you cool it, and you cool it down to 2 Kelvin. Now, it turns out that these experiments in those days could not be done at intermediate temperatures. Okay? And here's a good graduate student question. Why could you do this experiment at 2 Kelvin but not at 2.3 Kelvin? Okay? Think about it. So the point is that in those days when you're cooling this thing, you bathe your sample with helium. Okay? And if you shine light on ordinary helium, it boils. It is boiling all the time, but when it turns superfluid at 2.18 Kelvin, is it? It stops boiling, and then you can do your scattering experiment without things going crazy. Okay, so when you do this experiment, now notice that this is on a different scale. When you do this new experiment, then you notice that there is this A1G phonon is still there, but an additional thing appears. Okay, sharp additional things appears. In the E2G symmetry, another sharp thing appears, and these energies are very close, and they're very close to twice the superconducting gap of niobium diselenide. So there's this new mode. It's very sharp, and it appears irrespective of which symmetry you're looking at. And if you looked at the data, although this was not done quantitatively, it appeared that going from here to here, going from here to here, the intensity of this thing decreased. So it appeared as if this fellow was making its appearance at the expense of this fellow, okay, and also this at the expense of the amplitude of this. So this was the experiment. So let me do a little bit of theory. It's more fun talking about experiments, but there was this there's this great pianist who actually does most of his life composing for music for Hollywood, but he says sometimes I have to play classical music because my mother took me to all those classes, to the pianist classes for 15 years. So I'm going to have to do a little bit of theory for discussing these experiments. So we are in a superconductor. A superconductor is an object which is characterized by a complex order parameter. Okay, it has an amplitude and it has a phase. Right? After all, we have to carry currents, and currents quantum mechanically are related to the gradient of they have to be related to, current is psi star grad psi, so minus, and the Hermitian conjugate. So it is related to the gradient of the phase, and that's why Ginsberg and Landau introduced this complex order parameter for superconductors. And this, of course, is an order parameter which also describes superfluids. It describes superconductors. It describes planar antiferromagnets, two-dimensional antiferromagnets. It describes incommensurate charge and spin density waves. So all kinds of phenomena are described by a model with a complex order parameter, an amplitude and a phase. So if you have an amplitude and a phase, and if you want to do statistical mechanics with it, then even if you don't precisely know what psi means and what phi means, you know purely from grounds of symmetry that the potential energy that you can concoct with this kind of an order parameter has to be modulus of psi square, the first term, with the coefficient r, modulus of psi fourth with another coefficient, and if you're varying the psi in phase in space, it must depend upon gradient of psi square. That's how you're constructing a scalar potential. And now, if r is positive, then of course this is a simple parabola and is in all directions, and that doesn't seem very interesting. But if r is negative, then if I fix the phase, then it is a double well potential, okay, and the amplitude acquires a finite value, which is the minima of this object, right? Minima in this double well potential. But you see that as far as the phase is concerned, that is, if you travel in this direction, it is uniform. Okay? Now, of course, you need a microscopic theory for parameters r, u, and c. When r changes sign, that's, of course, the superconducting order parameter. And this thing we understand much more deeply now, following the work of BCS and Gorkov and etc. That if you're describing a superconductor, what exactly is this amplitude and what is this phase? Okay, we have a microscopic theory of it, and the microscopic theory says it is better, instead of talking about ordinary fermions with momentum k, spin up, etc., to make spinners, the Gorkov spinners, and we make these spinors. So now it's in some SU2 space, right? It's a space of Pauli matrices. And in the space of Pauli matrices, well, what is the charge density? It is, right, CK up dagger, CK up, etc. And that is in the tau 3 direction in the spinor. The amplitude, which is CK times CK, let us say, it's in the tau 1 sector, and there is a third sector, which is the phase. Okay? And then we can write down an effective Hamiltonian in this sector, which is the ordinary kinetic energy, which is just in the charge sector, therefore it's tau 3. There is in condensed matter physics, everything is very simple. It's really charge-charge interaction. So you see, you have charge-charge interaction, just a density-density interaction. And the genius of BCS lay in saying, let's take this horrible interaction and write what we like about it, and just write down this whole part in terms of a bilinear of these spinors in the tau 1 direction. Okay? This is a work of genius. You drop terms which are uninteresting, come to some conclusion, and say, if you included those other terms, it doesn't matter about the solution that you have, about the part that you have kept. That's the main part of the genius here, okay, of BCS. Okay, from our point of view, it will be interesting to note that this Hamiltonian, the BCS Hamiltonian, bears a one-to-one correspondence with the Dirac equation. Okay, and that would be interesting and important. And in fact, Nambu was the guy who first noticed that and tried to make it his life's work in particle physics, exploiting this analogy. Okay, now let's go back to this thing and talk about superconductivity or the gauge theory in particle physics in a simplified language. As I mentioned, in this direction, if you move in the phi direction, everything has zero energy. Everything has the same energy, which really means that if you slowly vary phi from place to place, the energy must go to zero as you make the variation slower and slower. Okay? Because all values of phi have the same energy. This is simply a statement that there must exist a collective mode at zero energy at long wavelengths. Okay? So this is the content of the so-called Goldstone Theorem. Okay? That if you have this, if you condense with a continuous degree of freedom and you have a phase variable, there must exist a mode which has zero energy at long wavelengths. Now, in the early 1960s, after the Yang-Mills theory was formulated, which is the same thing with extra indices and some extra twists. It's not in U1, but it's SU2. Everything looked wonderful, except this theory was predicting massless particles. It was predicting that there should be some objects which should have zero energy, except the only massless particles we knew in nature at that time, at least, were photons, and therefore this theory was rejected, although it had many, many good things in particle physics. However, in relation to superconductivity, there were certain things that were realized, because superconductors also do not have this massless mode. Okay? Superconductors do not. Superfluids do. That's interesting. But superconductors don't. And that is connected by the elementary fact that, as I mentioned, gradient of this phase is proportional to current. and current has to obey the continuity equation. So the time derivative of the density has to be related to divergence of J. So what that means is that any oscillations in phase had to be related to oscillations of charge density. And we knew from 100 years in condensed matter physics, well, at least from the 1950s, that charge oscillations occur at the plasma frequency. Okay, right? If you imagine you have a whole bunch of positive charges and negative charges, and you move your negative charges one way in relation to the positive charges, they will oscillate, right? Due to at the plasma frequency, which is a very high frequency, and that's because of the infinite range of 1/r Coulomb interactions. Okay, okay. Now this thing was missing in BCS theory because BCS theory was not in its original form was not satisfying this continuity equation. So people were giving a lot of grief to BCS those days, saying, "Oh, your theory is not even gauge invariant. It must be wrong." Okay, even though there were a few thousand experiments which were being explained. Okay, but there all these guys. Now the Russians were not bothered about it because within months of BCS theory, Gorkov derived the Ginsberg-Landau equation from it, and Ginsberg-Landau equation was manifestly gauge invariant and following this the continuity equation. So when I was told the story that around 1959 or so, Anderson went to Moscow and told at the Landau school, "Oh, I have made BCS theory gauge invariant." And they said, "Oh, but we already know it's gauge invariant." They were not impressed. Okay. So, but Anderson actually calculated and said that if you do a slightly better theory, you get this plasma. Okay. Now, so this is the Higgs mechanism. One has to distinguish in this business. There's Higgs mode, there's Higgs mechanism, there is Anderson mode, there's Bogoliubov mode. So Anderson mode, Bogoliubov mode, and the whatever this is, they are just one and the same thing. And then there is something else. So around 1964, on the same model, really just the U1 model, not even the SU2 model, there were a whole bunch of people working with the explicit mention by Higgs to Anderson work saying, "Gee, I'm making a theory of weak." Well, he was not even making a theory of weak interaction. He was making a theory of U1. In fact, that's an amusing story that he did this and then he went off in the direction of applying those ideas to strong interactions, and so did Nambu, and it turned out to be irrelevant in that context. But Higgs pointed out that there is also a scalar, and this word will play an important role in my talk, that besides this Anderson, Bogoliubov, what have you mode, which has moved to the plasma frequency because the weak interaction is coupled to electromagnetism, just as the superconductivity is made up of electrons, and electrons have a habit of repelling, therefore charge modes at the plasma frequency, that there should be some other mode. Now, the main hero to me in this whole business in particle physics are Weinberg and Salam, who took this idea, applied it to SU2 gauge field theory of weak interaction, and Weinberg and Salam predicted the equivalent of these modes to be the Z and the W to particles, because it's a somewhat richer theory. There are two kinds of plasmons, if you like, and then also used this amplitude mode. Okay, There's a lovely 3-page paper of Weinberg in Physrev letter around 1967-68, which has everything that you need to know about weak interactions. Okay? It predicts Z and W and the Higgs. Okay, so the interesting question is, why was this Higgs also not already discovered in the Landau-Ginsberg model? This is the amusing sociological point. Okay, so why was Higgs missed in condensed matter physics over the years? Now, to calculate collective modes, we need time dependence of equations for motion. Okay? Now, what can we do? We need time dependence. Ginsberg-Landau, when it was generalized to time dependent, said, oh, there must be some loss, because that was a theory near the transition temperature where loss of energy is important. So they put in a term with a coefficient lambda, which is real. And now this is what you put to calculate your effective Schrodinger equation. And you see this equation is, first of all, it breaks time reversal. And it is also particle-hole asymmetric. Okay? So in the Ginsberg-Landau dynamical version of Ginsberg-Landau, you put in a time dependence, which is time reversal breaking, dissipation. Okay, this is changing energy. And also, you can see that it is lambda is a real variable. See, one derivative with respect to time obviously breaks time reversal, and it changes sign under particle-hole transformation. Supposing, being condensed matter physicists, here is where the cultural difference comes in. You put in a Schrodinger equation. In Schrodinger equation, you have a real coefficient k, but you put an I, right? Schrodinger equation, you have an I. So this I is,
Lagrangian, not an equation.
the Lagrangian, sorry. So this I is odd under time reversal. This T is odd under time reversal. So this is time reversal invariant, but it breaks particle-hole symmetry. But supposing you make a Lorentz invariant theory, then you have two derivatives in time. Okay? In Lorentz invariant theory, you make, because time and space have to be treated equivalently in a relativistic theory, two derivatives of time. This is real. And now you see that this is both time reversal preserving and particle-hole symmetric. Now it turns out that Higgs mode only exists in this theory, okay, which is time reversal preserving and particle-hole symmetric. And if you are dumb and ignorant, like Littlewood and I were, and you simply try to do a microscopic theory in the collisionless limit, you automatically make a theory which is time reversal invariant and particle-hole symmetric. Okay, so that's how we got the Higgs. Okay, so amplitude and Higgs mode exists only in this case. Let me illustrate this by the following thing. So supposing I make small oscillations of amplitude and phase of order parameter. So this is my equilibrium value, and this is my instantaneous value at a point r, and I take the difference and write it in terms of an amplitude variable and a phase variable. And if you write down the equations of motion, you notice immediately that if this k1 is 0, then I have a distinct phase mode. I have no Coulomb interaction here, therefore I have this Bogoliubov mode. Okay, and you get a distinct amplitude mode, and the amplitude mode energy is related to square root of that parameter r, which determines the magnitude of the superconducting gap. But the moment you put in k1, the amplitude and the phase mode get mixed. Okay, so the moment you break particle-hole symmetry, you are screwed. Is that allowed to be used? Okay. So for k1 equal to 0, distinct amplitude and phase mode. For k2 equal to 0. Now, supposing you make a theory with k2 equals 0, the Lorentz invariant part, you put it, then you'll see that the two modes are degenerate and completely mixed, and this is what people were usually getting. etc. Okay. Now, supposing you are uncharged superfluid. So I was making a theory of, so there was never a Higgs mode to be talked about in superfluid helium, either helium-4 or helium-3. Okay, and the point is that they are very particle-hole asymmetric. Okay, so supposing you take a helium atom, how particle-hole asymmetric it is? It's particle-hole asymmetric by what's the binding energy of the first state of helium? 52 eV, right? That's how asymmetric it is, and we are going to be dealing with 10 to the minus 4 eV physics. So in superfluid helium is very particle-hole asymmetric. It has no amplitude mode. Okay, so the way we do Schrodinger equation in condensed matter physics for helium is perfectly okay. That's called the Gross-Petersky equation, the equivalent of Ginsberg, Landau, time dependent. That's perfectly okay. Okay. Supposing you do cold atoms in a lattice, then if there are people who do cold atom, this Schrodinger parameter or mass parameter is generally non-zero, and amplitude and phase exist, but there are isolated points in the cold atom phase diagram where you have particle-hole symmetry. In superconductors, you break particle-hole symmetry only by the order of delta over EF square. Okay, that's a very small number, and therefore Higgs exists. So Higgs exists. It has an energy of the order of twice the superconducting gap, exactly twice the superconducting gap in weak coupling BCS theory, but no reason why it should be exactly that when interactions are included. The phase modes are pushed to the normal plasma frequency. Okay. So this is why we said these are the Higgs. Okay, we didn't know the Higgs. We were ignorant, and in education in United States, you learn condensed matter physics and you don't learn particle physics, even if you are a theorist, and therefore we just called it an amplitude mode, which is what the mode in high energy physics should really be called. Okay. Anyway, so however, the main interesting thing that I want to say is that just saying I got the energy of this mode is completely uninteresting. Not only the theory is dumb simple, but that does not explain the essential feature of how it was discovered. Why is this mode a daughter of these fellows? Okay, because now you can do Raman scattering in lots of materials, and a few of them you discover, and when you discover there is another mode lying close by, and not in others. Okay, so the most interesting aspect of Higgs is under what experimental condition can you discover it? Okay, and that's what I'm going to try to explain. I already mentioned this. Why is it seen in this compound and not at others? Why is this so little damped? Why is the same thing seen in different symmetries? Okay. To answer these questions, you have to ask, what is the eigenstate of the amplitude mode? How can one couple to it? And there we come to an interesting point. It's almost impossible to couple to it. Okay? Because this mode has the same symmetry as the ground state. It has no charge, it has no dipole moment, it has no spin, it has no angular momentum, or anything else to which... Dark matter. Sorry? Dark matter. It's dark matter, okay? It's dark matter. So how do you couple to it, okay? And that is really the amusing part of it. And again, we were too dumb to realize what we were doing, but we found a way to couple to it, okay? Here is my lattice vibration, and we said, oh, this lattice vibration must excite this Higgs, okay? And when that happens, you see, if you have a thing like this, and you can couple to this by Raman scattering, a daughter will be born when this mode exists, and this daughter will come precisely at the expense of this, meaning the weight of the phonon above the transition will become equal to the spectral weight of the phonon plus this object below the transition. So there's a prediction. You can, okay. Well, what does this mean? What is this vertex? How is that possible? And that is possible only because the ground state is number, non-conserving. Okay? This is interesting. This is the only really interesting thing that I'm going to tell you, a cute thing in the physics here. So you see, you have a phonon. See, and a phonon can only excite a particle-hole pair. It's a density. It can only excite a density. Cooper pair, this Higgs mode is certainly not a charge density, right? So you can excite this particle-hole pair, K plus Q. But you can take this fellow and say, oh, I'm going to propagate a Cooper pair in this direction. And now suddenly I have the symmetry of the superconductor. How can I do that? I can do that if there is a vacuum expectation value here of this object tau 1. Sorry?
Is it excitation of
So this is going to be my Higgs, which is a mode in the particle-particle channel. And how did I convert from particle-hole channel to this object? Only by saying that I have a vacuum expectation value here so that I do not have to conserve particle number. The ground state in a superconductor is a linear combination of n plus 2, n minus 2, n plus 4, n minus 4 with different amplitudes. Okay? And so I have an expectation value. Therefore, this vertex becomes allowed. This also moves the amplitude mode below 2 delta slightly, and therefore removes damping if I have an S-wave superconductor. Okay? So the prediction from this is that the integrated weight of the phonon plus Higgs should be conserved in the experiment. Now, this, of course, could not be tested by Miles Klein and his students with technology of the 1980s, where when you're shown light and you were cooling by putting helium, you could do only the experiment at very low temperatures in the superconducting state. Otherwise, helium would start boiling, okay, and your scattering would be screwed up. But these days, they can cool by other ways, and the Raman scattering intensities have improved. They can detect the few orders of magnitude better. So this experiment was done by in Alain Secuto's lab by Mariod-Miasson, and it's the same material. And now this has been done in other materials. And you see here's 8 Kelvin, and you see this phonon. And now you cool and you go below the superconducting transition, and the amplitude of this decreases, and the amplitude of that increases. And if you look at the integrated weight of the stuff, that is, if you take out the average, you see that the total integrated weight within the error bars is conserved. Okay? So it means that you cannot directly couple to it, but you can borrow weight provided you have a vertex which is number non-conserving. Okay? Why is this the Higgs? Now, around 1982-83, I went to University of Chicago, and I gave a talk on this, and I'd actually spent a year as an assistant professor at University of Chicago in 1970 for a year, and then ran back to Bell Labs. Okay, didn't stay around there. And so I had come to know Nambu, and when I presented this talk, Nambu was in the audience, and he laughed and said, ha, 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 you have discovered the Higgs. And I thought he was joking. I thought he was making fun of me. And I thought of helium, and I said, there's no Higgs in helium, so what is he talking about? Okay, so but then There was a book written in 1997, edited by Lillian Hodgson, in which the book is called The Rise of the Standard Model. And all the greats of the Standard Model have articles telling how they had formulated or helped formulate the Standard Model, and including the articles by Peter Higgs and Nambu. And Higgs has the statement, whom I've never met, the existence of the characteristic massive spin zero mode had not been noticed by Anderson or by Angler and Brout. First, he's making sure everybody knows that the massive spinless mode is his and not Anderson and Brout. And then he's saying, indeed, the theory of what particle physicists would call the Higgs mode in a superconductor was not published until 1981, after it had been detected in the Raman spectrum of superconducting niobium diselenide, and this was the experiment by Klein in reference to Littlewood and me. And I said, my God, these guys are serious. And Nambu had some similar remark. So I said, okay, I better learn some particle physics. So I learned the rudiments of it. And I'm going to come to aspects of that. Now, there are other ways of coupling to the amplitude mode. So there's a recent experiment in Japan. It's kind of violent experiment. You take this superconductor and they have done it in various other superconductors, and you hit the superconductor with some megawatt, terawatt, God knows what, femtosecond pulse of terahertz radiation. You beat the heck out of this, and then you probe it by another object, and then you find that there are oscillations as a function of time in the absorption rate of another photon. Okay? And the oscillation is at twice the superconducting gap. Okay? So what's happening here is that you're doing nonlinear coupling. So what I was talking about was linear coupling is not possible by ordinary photon absorption, right? So here, what they're doing is nonlinear coupling, meaning that we always have this term, right? The gradient minus the vector potential times psi square, and this A is your, you shine your horrible, your femtosecond pulse, and when you do that, you are generating a term A dot grad phi psi, and now you see you are coupling with A dot grad psi, you're coupling psi. Okay, so psi is psi, yeah. There should be another. Yeah, sorry, there should be another thing here, but it won't matter. Okay, and now you come with your second pulse, and so what you're seeing is a nonlinear effect created by the first pulse, and you can see this thing. Okay. Now, it turns out that it is not completely true that you cannot couple to the Higgs. Okay? So here is another way to couple to Higgs. You cannot couple to a superconducting order parameter except through another superconducting order parameter. Then it's easy. So you can take a superconductor and let's say you want to understand this superconductor and you know this superconductor, and they have a coupling, Josephson coupling of this form. So if you somehow oscillate things on this side will oscillate. Okay? And you can do that by kind of a Josephson effect, and you can even study the omega and k dependence of it by applying an in-plane magnetic field. And there are some peculiar experimental results by Alan Goldman in the 1970s when he was discovering some other modes where you also see some high frequency modes, and they may be probably that. And this is some experiment done. How am I doing on time? Okay, so I'll skip the cold bosons, and let me just accept to make a remark that you can, if you have a superfluid where there is particle-hole symmetry, which cold bosons do at what happened to the cold boson? They do at these points. If you're doing your, is it this point or this point? This point. if you do experiments near these points, you have particle-hole symmetry. You see you are filling up, you're changing the chemical potential and number of particles per site on this cold boson lattice is going from 0 to 1. And when you're at n equal to 1, you have particle-hole symmetry. And if you do your experiments around here, then you should be able to see Higgs. And there the thing would be even simpler. Here I had to do this thing, but now supposing you shake, see, to excite the Higgs, you have to shake the condensate, right? So when in the LHC, when they are seeing the particle physics Higgs, they are shaking the condensate, which is really saying you're shaking the foundations of the present day universe. You really, the condensate, the electroweak condensate, which permeates everything and is everywhere, you're locally shaking it, okay? My God, if you come up with $10 billion and a teravolt pulse, you can shake anything up to a point. But here, supposing you have a superfluid and you shake it, then since there's an expectation value in the superfluid of just this boson, you can excite this B dagger, because B dagger B is what you do with your density is what you do when you shake, but you have this expectation value. So that's even cuter, and you have some coupling constant like that. Okay. So these are really just arguments with condensed matter physicists about why most of the things that you see should not be called Higgs, but it's become fashionable since 2014 or 15 to call anything you see Higgs. But there's only, you have to be locally gauge invariant and you have to have particle-hole symmetry. Okay. Wow. So let me come to the last part of my talk, the sort of the most ignorant part of my being. So here is how this is CMS, or is it the other one in Geneva, and so the Higgs was discovered. The Higgs in condensed matter physics is being discovered these days in various people's labs in a little apparatus like that with actual human beings of this size in the same room. And you know about this is the first discovery of Higgs. See, and look at this. This was 5 sigma deviation. I do remember asking, since I'm very troublesome, I have always been troublesome, asking my high energy experimental friends, do you really believe in this point? And my God, they had very, very good reasons to believe. One of the things you begin to appreciate about particle physics as a condensed matter physicist is how fantastic technical developments are in particle physics in experiments, and how precisely they make their statements. Even more impressive than the Higgs, to me, was the fact that they can actually calculate this background to a part in 10 to the 3, 10 to the 4 from known physics from earlier thing. I mean, really, these guys are good. Okay? They're as good as condensed matter physicists. Many ways better. Okay? Many cases better. And this was the Higgs that was discovered. And what I wanted to say was that at least in one of these things, and by now I have even forgotten, the Higgs is only excited because of the fact that there is an electroweak condensate, and you are really breaking the equivalent of number conservation. That's how you do this. So I was very interested in that. I said, I do not find it, from my point of view, at all impressive, the statement that Higgs gives mass to all the particles. First of all, it's an incorrect statement. It only gives mass to leptons. And I'm not so concerned about giving mass to particles. What I thought was most interesting was that the discovery of Higgs was a proof that there is an electroweak condensate. And my particle physicist friends said, but we already knew that because W and Z particles would not exist but for the electroweak condensate. And I want to make a remark about that. And that shows the sort of the difference between condensed matter physics way of thinking about condensate and the particle physics. Okay. So let me contrast the theory of superconductivity with electroweak gauge theory. Can condensed matter physics say anything helpful? And I can give you an answer right away, no. Okay? I've tried with some clever particle physics friends to say something useful. I haven't been able to. Okay. Now, the big difference is that we are, in condensed matter physics, a very rich field experimentally. Okay? And we have a theory of matter, or let's say metals, from high energy to low energy. We have a theory of the normal state of metals. Okay? And therefore, we have knowledge of interactions and complete low energy interactions. So we have a complete theory of superconducting condensation in 75 years of experiments. Okay? In particle physics, prior to 2012, there were few experiments, few new experiments, or few totally new experiments. They were, of course, determining all the parameters in the standard model with increasing accuracy. Now, the level of the theory in particle physics, as I understand, is really at the level of the Ginsberg-Landau theory. Okay? It's somewhat more decorated because it's SU2 or SU3 or what have you. But there is no knowledge of the uncondensed state, what we think of as the normal state of metal. There is really no knowledge of it. And how is that knowledge possible? It's not possible because the temperature of the electroweak condensate is 250 GeV, or estimated to be about 250 GeV. So you would have to, like in the case of niobium diselenide, I do an experiment about 7.2 Kelvin. I'm in the normal metal. I understand everything about it. And then I go down below. Okay? So what happens is that in the present theory, which is the Ginsberg-Landau level, Higgs exists, but above the, you remember that parameter R, which made you a double well potential? If R is positive, there is a single parabola. Well, in a single parabola, there is a bound state of amplitude. So as far as they are concerned, as far as the particle physics is concerned, Higgs exists above the electroweak condensate, but if you do not have this double well, you cannot think about going around the ring, and therefore they don't have a W and Z. So they think that W and Z exists because of this double well, and you're going around there. Okay? But my God, the equivalent of W and Z in condensed matter physics is the plasmons. And we bloody well know that plasmons exist in the normal state. Okay? So if I had only Ginsberg-Landau theory of superconductivity and nothing else, if I didn't have 100 years of experiments on normal metals, I would not dream of plasmon existing in the normal state. I would not be able to do any experiments. Okay? So that is why they tell me that W and Z will continue to, W and Z will become massless above, whereas we know W and Z, or the equivalent plasmons, is the massive plasmon mode. It's because we have, so there's a big divergence of the theory at a fundamental intellectual level in the energy scale about 250 GeV. There's no difference at a fundamental conceptual level between electroweak condensation and superconductivity for the electroweak theory below 250 GeV and superconductors below their transition temperature. Okay? But The high energy thing, there are no experiments. Okay? So, summary. All superconductors are almost particle hole symmetric. So superconductors, amplitude modes must exist in all superconductors. It's a scalar. It's an oscillation of number density, not a charge density. To detect it linearly, we must shake the condensate to be freed from conservation laws. If detected, it's a proof of the condensate. The condensate of particle physics, which is really the theories at zero temperature, has relation to superconductor, but the normal state is quite different. Well, we don't know what it is, okay? Is that a fair thing to say? We don't know what it is. And that's where I'd like to end my talk. Thank you.
Questions?
Could you speak up?
I'd like to make the attempt to fill in a little bit of the gap between low energy and high energy by going in the strong interaction, nuclear physics perspective. And there, our sort of understanding is that we also have scalar condensate, 54 pairs. We have the Higgs boson, which is so-called sigma method. And we can probe it experimentally by doing heavy ion collisions and heat the matter to the relevant scales where we melt those condensates.
Yeah. What I'm told by people in your discipline is that QCD is in much better shape than electroweak. From yeah, I agree with you. Yeah.
You can measure actually how the mass dissolves
Yeah.
from the electric
Yeah. The question is just the electroweak theory by itself seems to have hit an impasse, especially as there seems to be nothing new being discovered at LHC. I understand. I hope that's no longer true in a few years. But unless there are, the smartest people in the world are working on all that sort of stuff, but unless there are no new experiments, no new experimental results, one will simply go on speculating like mad and doing fantastically beautiful mathematics. But mathematics has millions of conceivable universes, and we are living in only one. So it's hard to narrow down from a 10 to the 80 possible theories to one.
There were collective modes that were seen in superfluid. Well, first of all, I wanted to thank you for a very, very beautiful lecture. I've really enjoyed it, and it connects so many things. In fact, Brout and Angler were working directly across the hall from me when I was a young faculty member at Cornell. But in the 80s, we found collective modes of helium-3.
I'm well aware of those.
Which also would probably fit into your model.
Yeah. So in liquid helium-3, which Professor whose superfluidity Professor Lee discovered with Richardson and my former colleague Doug Osheroff. It was Doug Osheroff's thesis, and then he came to Bell Labs. There are collective, the helium-3 is slightly more complicated superfluid order parameter. There is, since it's angular momentum 1, spin 1, there are modes of the angular momentum and of the spin.
The sound. The ultrasound measurements were done.
Yeah. So there are variants of this. They are like saying that in particle physics there are many varieties of Higgs.
They obey the NAMU identity.
Absolutely. Yeah. So I should tell you, since David Lee is here, the most mortifying experience of my life when these people discovered liquid helium-3, Anderson and I started working on trying to understand the modes that these people discovered. The nuclear resonance frequency had shifted by a certain amount. We had understood that it was shifting, it was superfluid and it was shifting due to dipolar interactions. And then we did a calculation, which Anderson is absolutely sure I did, which was completely wrong, okay, and therefore missed out explaining Richardson-Lee Ostroff experiment, which Tony Leggett really did. Yeah. So, big loss of my life.
I have the following question. Because of neutrality, the excitation with your Higgs excitation is a combination of oscillation of superconductor and normal part. Because superconducting part is charged. Wires are charged, so that should be normal part also participate in that. And then I would expect that the gap is bigger than 2 delta or something like that.
Okay, on the first part, I do not agree with you. Okay, this is an issue which I had to, and I can. We should discuss that privately. And secondly, if it was about 2 delta, it would be damped out to death. We know with precision experiments it's always below 2 delta, and we understand why. Okay, and on the first part, it's a pure mode of the amplitude of the superconducting order parameter, nothing else. There's no normal state involved.
How the neutrality is?
Sorry? Because a Cooper pair has no charge. It's not an...
It's bound state of 2 electrons.
No, it is not.
No.
Okay? Really, it's in the tau 1 sector as opposed to tau 3 sector. It's a completely orthogonal object. And this is one of the things that we had to realize, that there is really, in a gauge invariant theory, there is no coupling between the normal. The moment it is not particle hole symmetric, or you have to put in dissipation, the things get mixed in, as I showed through those simple equations of motion. But otherwise, in the limit of collisionless and particle hole symmetric, completely orthogonal. I can assure you.
Chandra, the other way to answer is that there is no Hall effect for Cooper pair.
There is no Hall effect for Cooper pair. Yeah. I think there would be if you... there would be some aspect of Hall effect for Cooper pairs right close to the phase transition. This would be an interesting thing to investigate. Yeah.
Say that basically the Higgs mode should exist in all superconductors. But as far as I understand, it's not experimentally observable in all superconductors. Is that due to, like, do you need a specific Raman mode, or is it more to
Yeah.
superconductors easier to shake up the current state enough in the coma?
So this is something I can explain. Now, the weight transfer from here to here depends upon some coupling constant between this fellow, because of that lack of number conservation, but it inversely depends upon the difference of frequency of these. Okay? You see, if you have two resonances of somewhat different frequency, the weight transferred has to go as 1 over the frequency. So in the case of niobium diselenide, we were very lucky, or they were very lucky, that this frequency is not far from this frequency. That is not a usual situation. There are other materials known, like the so-called A15 compounds, where also there are optical modes at low frequency comparable to twice the superconducting gap. And again, it is seen there. And what's more this statement is can be made even precise, because just in the last year, my friend Mariade Miasson in Paris has done experiments in which you apply pressure to the same compound. And as you apply pressure, this mode goes up. Okay? The phonon mode goes up. And as the phonon mode goes up, the amplitude of this thing systematically decreases.
Chandra, is this Raman also shaking?
Raman is really creating the phonon mode.
Yeah, but it's also presumably
And
shaking by just one condensate by just one part by the other.
Are you thinking about the term in the action which is going as rho times a square? Is that what you're thinking about?
Presumably, because I'm thinking about two photons, one is coming.
Yeah. Now, so the answer is in principle yes. The trouble with that is that also excites a incoherent spectrum of normal state excitations. So here is a material, niobium disulfide, which is the same structure as niobium diselenide, okay, except it does not have that close by optical phonon. And if you do the experiment in that, and it becomes superconducting, and if you do the experiment, you see here is the niobium diselenide experiment, here's the niobium disulfide experiment. You distribute that whole thing over a very wide energy region, and you get the extra spectra, which is just a weak enhancement over this, because you're exciting a whole bunch of other things simultaneously. At least that's my understanding. But in principle, no reason why not. Okay.
Any other questions? All right, let's thank the speaker again. You need to take off your microphone.
Huh?
You need to take off your microphone.
Thank you
so much for this. This is great.
Thanks, sir. Good to see you again.
It's nice to see you. I just was wondering about these collective modes. I mean, there were actually two collective modes that were observed in helium-3. but they
One
were
was
below
called
the gap.
clapping mode, and the other
Yeah,
something
there- no,
else.
there's a
See
gap.
David's paper. David has paper on this.
This was
Дали меня подвинуть.
and what happened was that there was one at about, I don't know, they were well below the gap. They were well below, that means that